Okay, in this video I'm going to continue on with exercise 6a of the book Fundamental Applied Mathematics. We're on page number 156 and the question is 6. It reads, a man pulls his son, who is in a toboggan, across horizontal snowy ground by means of a light rope. The son and toboggan have mass 20 kilograms and the coefficient of friction is 1/7. The tension of the rope is 50 newtons and the rope makes an angle A where tan A is 7/24 with the ground. If the toboggan moves a distance of 30 meters, find the normal force, the friction force, the tensional force, the work done by the tensional force, the acceleration and the power output if the man did this over 20 seconds. So I've sketched the motion in front of you. The first thing we're going to do is to resolve the tensional vector into its component unit vectors, because remember, we need to know how much of it is going in the direction of motion and how much of it is going perpendicular to it. So we're going to get the following. Draw this parallel to the I hat, this parallel to the j hat, put them at right angles. We know of course that t is equal to t sub x I hat plus t sub y j hat. Alright, so t is equal to, and it's going to be t times the cosine of a for the I hat component, and if a is equal to 7/24, then the component, the cos of it, excuse me, is 24/25. So it's going to be 50 times 24/25 in the I hat direction plus 50 times 7/25 in the j hat direction. So let's just find out what those are. 50 multiplied by 24 divided by 25 gives an answer of 48 I hat plus 50 multiplied by 7 divided by 25 giving 14 j hat. Alright, so that's pretty straightforward stuff. The thing is, however, we need to apply Newton's second law in order to work out what the normal force is. And you might say to yourself, well, why is that? Why isn't it just 20g? And the answer is because the tensional force is also providing a force in the j hat direction. So this time, it just apply Newton's second law and we'll see what happens. So go in the j hat direction, you're going to find that nj hat plus 14j hat minus 20g hat is equal to its mass, which is 20, times its acceleration. Now the toboggan clearly isn't going to leave the ground, therefore the acceleration in a vertical direction is going to be equal to 0. So we're going to say that n is equal to 20g minus 14 in the j hat direction. So let's just find out what that answer is there. So 20 multiplied by 9.81 divided by minus 14 gives an answer of 182 newtons, which is correct. That's equal to the normal force. All right. So we're doing pretty well so far. The next thing we're asked to do is to find the frictional force. And at this stage we know that the frictional force is equal to the normal force times the coefficient of friction. So that turns out to be 182 times 1/7, giving an answer of 26 newtons. So it's 26 newtons in the negative I hat direction, if we're assuming that the toboggan is going in a positive I hat direction. Right? So next, what have we got to do? The third part of the question states to work out the work done by the tensional force. So how do we do this? Well, work done is equal to force times distance, or work done is equal to force times displacement, in fact. So the first thing we've got to do is work out the overall force in the I hat direction. I'm going to call it F I hat. That's the overall net result of the force T being applied to it. So let's apply Newton's second law to the I hat direction. We're going to get the following. You're going to get 48 I hat negative 26 I hat is equal to its mass, which is 20, times its acceleration, which is just a. So let's just work out what that is. So we have 48 minus 26 divided by 20, given an acceleration of 1.1 meters per second squared. Alright, so now we have the acceleration. But we want to work out the overall net result of this force. So the net force is equal to 48 I hat negative 26 j hat okay, is equal to 22 I hat. So the overall result of having this tensional force here is that there is 22 units of force moving in the positive I hat direction. So let's apply this, and we'll get the following. Work done is equal to 22 I hat times the distance, or the displacement, excuse me. We're told the displacement is 30 meters, so I'm going to say it's 30 meters in the I hat direction. Okay, and we're going to get a work done of 30 multiplied by 22, giving 660 newtons, or 660 joules. That seems incorrect to me. There must be something else I'm missing here. Just bear with me just one moment. Okay, so 1440 divided by 30, 48. Oh, I know, I'm after copying my mistake. I worked out the work done by the net force on the body, but that's not what we're asked. We're actually asked, I'm just going to write it down, we're asked to work the work by the rope on the toboggan. Alright, what I worked out was the total work done by the net force, but we're not asked the work done by the net force. The work done by the tension on the toboggan is 48 units in the I hat direction times 30 meters, giving 1440 joules, which is correct. So I see my error there, okay, and I hope you hope that makes sense to you. The next part we're asked to do is find acceleration, which I've already done. And finally we're asked to find the power output of the man if it took 20 seconds. The power output if it took 20 seconds. So how do we do this now? Okay, I just trying to think about the best way to do this. Okay, so if we have, let's think about it this way. Power output is equal to work divided by time, or the average power anyway, is equal to the work divided by the time. So in this case it's 1440 divided by 20 seconds, giving a power output of 72 watts. Okay, so yeah, that's all I've got to say about that. Just be careful about what you're actually being asked. We are asked to find the work done by the tensional force on the rope, not the work done by the net force on the rope. Thanks for watching. Please pass it on to your friends and subscribe to my channel.